This is the Chapter 5 mixed FIP, and we have the building moved several blocks, 36 dollies, mass of the building, 1.45 times 10 to the 6th kilograms. If 1 times 10 to the 2nd megajoules of work was done, notice what I've underlined there, to overcome the force of resistance that was just 2% of the building's weight. How far was the building moved? So the work, we have to look at the work that was done. You have to figure the work was 0.2% of the force that was used. So the force was force of friction times 0.02.
Oh, so the force is just 2%.
Yeah, 2% of the weight. So that's what everybody missed who missed this, I think, was they forgot to factor in that 2% thing.
I didn't multiply gravity.
In this case, because it is moving, I mean, we're told it gets moved. So the work and the force, the net force, are in the same direction, so it's cosine 0. So this force, then, is the force that you divide the work by. And we're given the work, so we have the work that was done divided by the force that was used, and that divided out will give us the distance. You can see my erasure marks on this. I had screwed up initially, and I divided by 0.2, 20%. No, or multiplied by 0.2. No, try 0.02 is 2%. So I knew it was a decimal error, and I kept dividing it by the same thing, and I kept getting the same decimal error. But I knew I was wrong. It took me a little while.
I didn't think about the acceleration.
Well, because it says that it was 2% of the building's weight, and of course weight is force of gravity. So.
Yeah, I thought building's mass instead of building's weight.
I did it right, I just didn't realize, like, the wording in it.
Number 2, we've got a big old polar bear. He's running at you. You stop to calculate his KE, which means that you die. So max values for mass and velocity, you have to do a conversion, obviously, from kilometers per hour to meters per second. And that gives you a kinetic energy of 8.2 times 10 to the 4th joules, or 82,000 joules. It's a lot of energy in one big old running male polar bear that you don't ever want to see running at you. Okay, so you get 8,200 joules. Lots of people got this one. We're all good? Questions? Okay, for number 3, there were 2 answers here, which is how I got the whole thing out of 6. We have a box with some mass. It's being pulled up a ramp. Why do we keep pulling boxes up ramps? Because they're there. And the first thing we're asked is the force done by, the work done by friction. So that's going to be force of friction times cosine of theta. Theta here is 180 because friction is doing work in the opposite direction that the box is moving. So the angle between the motion and... you had to do a little bit of sum of forces to get your force of kinetic friction. And what you had to remember is, of course, and this is sort of cut off, force kinetic friction is going to be mu k Fn, and then if you did a quick little sum of forces on the y-axis, Fn is equal to mg cosine 16, mass gravity cosine 16. So a lot of people got this part right, that the work done by friction was negative 690 joules, so that went well. The second part was slightly tougher, and don't forget how I say that there are lots of different ways to get the answer.
How did I get that the right answer?
Well, so here's the interesting thing. There are at least 2 of you who did a completely different path. I think it's a little bit more complicated, but that doesn't mean it's wrong. And got a slightly different answer, so we're sig-figged off.
Yeah, I feel like one of them.
And so here's what I think is the easiest, most straightforward way to get something like this. Remember that delta KE is equal to the net work, which is equal to the net force times distance times cosine of theta. This thing is moving up the ramp, so the angle between the net work and the movement is 0, so we can get rid of the cosine theta. So then KE would be equal to the force applied minus the force of gravity on the x minus the force of kinetic friction times 6.5. So I went in and there's our force applied. I factored out the mg here. So I have 42.9 times 9.81 times quantity, and this is like tons and tons and tons of brackets and parentheses nested together. Sine 16 minus 0.261 times cosine of 16. What I get for, and then all times 6.5. What I get for the delta KE is 24,177 and change joules. Sig figs to 24,000 joules. And a lot of people came up with a 23,000 joules, and we'd have to go back and comb through the numbers. They may, because a lot of them figured final velocity, and
I solved for net work.
let's comb that one together, because I may have made a mistake, you may have made a mistake. One thing, and David just mentioned it, is the risk of circular numbers. When you're calculating one value to plug back into another value, you can end up in a self-reinforcing circle, and you don't want to do that, because then, oh, look, it all checks out. Well, yeah, that's because you just proved your own, you proved your own point. So let's look at that more closely, but let's look at the other two first, the last ones. Okay, so we've got this little well-constructed loaded mole trap, and it's out in the yard. Spring which slams the door shut, it has a spring constant of 475 newtons per meter and is deformed by 3.5 centimeters. If it moves the door to the trap 5 centimeters to close it, how much work is done on the door? What you had to think about was that the force of the spring is the spring constant times the distance it moves. There are 475 newtons of force in that spring per meter, but the spring is only deformed by 0.035 meters. This was kind of a challenge question. It was a little bit outside. You had to kind of think flexibly on this. If you look at a spring constant, any spring constant is the number of newtons of force per meters of deformation of the spring. Right. So for every meter that you deformed this particular spring, now that's not saying you can deform the spring by that much, you would generate 475 newtons of force. You're deforming the spring by 0.035 meters. So when you multiply the spring constant by the number of meters of deformation, what you get is the number of newtons of force you should generate. So, yeah, it's not something that we talked about explicitly. Like I said, this was kind of a stretch question, and I don't actually know that anybody got it. So this used to be one that was on the test, obviously. Like I said, I scavenged this off the test. It was a stretch question that you saw there, and, either you could, stretch and put it together, or you skipped this one, which lots of people skip this one. So we then have to take, I'm just going to keep doing this, the force generated by the spring when it snaps shut times the distance that spring moves the door, which is 0.05 meters, and we get work done on the door of 0.83 joules. Not a lot of work, very small amount of work, but it's a very small distance and a very small door. Yay! So this is really simple. It's conservation of mechanical energy. You've got initial gravity, initial kinetic, final gravity, final kinetic. We get 18 meters per second. Okay?
Part of it is knowing that it's a fib. If I get it wrong, it's just
Okay, we'll finish looking at number 3 in more depth tomorrow. That's it.